Good morning. We the team, the Dream Crew, is here to present about our proposed digital twin Smart AC which comes under the topic Smart Machine. Let me introduce myself. My name is Abarna S, the team leader, and my team members are Abby Anthony, Esther Thomas, and our next team member is Fasana Rahim, but she is not here due to some health issues. The main objective of our proposed system is to develop a digital twin of the air conditioner that provides the real-time monitoring of the system that predicts and alerts the user about any maintenance needs and before the fault actually occurs. And also it auto-configure the system to an optimal temperature based on the room temperature. Now, let me explain the normal working of the air conditioner. The main parts are compressor, condenser, expansion valve, evaporator, and a blower fan. The working starts in the compressor. The compressor starts compressing the refrigerant or gas into a high pressure and high temperature gas. This high pressure and high temperature refrigerant is then moved to the condenser. Inside the condenser, the phase of the refrigerant is changed from vapor to liquid, and this condensing liquid is then moved to the expansion valve. Inside the expansion valve, the pressure of the refrigerant is lowered and it is then moved to the evaporator. In this section, it will take the air from the room and the heat from the air is absorbed by the refrigerant. The blower fan will circulate the cool air to the room and the refrigerant changes its phase from liquid to vapor in the evaporator and it is then moved to the compressor. This cycle repeats continuously till the air conditioner is turned off. The next is common AC faults. The common AC faults are dirty filter, refrigerant leakage, fan complaint, and thermostat setting. Now, technology considered. It consists of several components or sensors that we are used in our proposed digital twin. The first one is LM35 temperature sensor. It is used to determine the coolant level and also it is used to check whether motor is overheating or not. The next one is DHT22 temperature and humidity sensor module. It is used to measure the room temperature. The next is infrared obstacle avoidance sensor module. It is used to detect dirt in the filter unit by measuring the IR light intensity. The next is tachometer. Tachometer is used to measure the fan speed. The next is one of the most important component in our proposed system. It is Arduino Uno development board. It is used to retrieve data from the sensors and store them in ThingSpeak via a Wi-Fi module. And also it acts as an interface for integrating various components. The next is LabVIEW software. LabVIEW software is used to create the mathematical model of the proposed digital twin Smart AC. Next is ThingSpeak. ThingSpeak is an IoT platform to collect, store, analyze, visualize, and act on data that come from various sensors. The next is Android Studio. Android Studio is used to develop an Android application that acts as a user interface through which the user receives the notification and also helps the user to monitor the proper working of the physical system. Brief description of the solution. LM35 temperature sensor is placed in the suction line of the condensing unit to determine the coolant level. If the temperature in that area is between 50 to 60 degree Fahrenheit, then the refrigerant level is normal. If the refrigerant level is extremely low, it can be a leakage issue. DHT22 temperature sensors are placed outside the indoor and outdoor units to determine the inside and outdoor temperature for predicting an optimal temperature. The issues related to air conditioner fan can be either due to motor complaint or due to capacitor complaint. LM35 temperature sensors are placed in the fan motor. If the temperature reading is above 40 degrees Celsius, it indicates an overheat, which was most probably a capacitor complaint. Tachometer placed near fan blade determines the fan speed. If the readings are below 800 rpm, it indicates a fan complaint, which may be probably due to a motor failure. Infrared obstacle avoidance sensor modules are placed in certain parts of the filter. When the transmitted light waves are reflected back, the reflected IR waves will be received by the receiver tube. If the intensity of the light received by the receiver tube is extremely low, it indicates dirt in the filter. An alert message to clean the filter is sent to the user by the digital twin. Minor thermostat problems can mimic more serious issues with HVAC systems and directly impact cooling system performance and comfort. Most thermostat malfunctions cause sudden changes in the performance of the cooling system. Therefore, proper monitoring of the thermostat is done. If the AC does not stop running even after reaching the set point, it indicates some fault with the thermostat. Next section will be handled by AP Anthony.
Now, let's see the mathematical model. For creating the mathematical model, we have used LabVIEW and ThingSpeak. Now let's see what they are. LabVIEW is a simple software that is used to create virtual interface. There are many built-in VIs available in LabVIEW, which makes it much simpler to use. And ThingSpeak is a web-based server that lets you to collect sensor data in the cloud and develop IoT applications. It is compatible with any programming language, which means it is easy to store data and retrieve data. We can store and retrieve data using RESET APIs or HTTP. Now, for better understanding, we are going to see each of this mathematical model in a screen recording. Let's watch. Proposed digital twin monitors the refrigerant level, dirt in the inside and outside filters, fan issues for both inside and outside fans, and thermostat complaint. For simplicity and better understanding, we have divided the entire mathematical model into 4 modules: the refrigerant module, fan module, filter module, and thermostat module. When the AC is turned on, all the sensors get activated and the sensor readings are sent to the cloud. Our mathematical model works by retrieving the values stored in the cloud and by doing appropriate calculation. First, let's see the working of the fan module. This is the front panel of our fan module. We have a screen to display the messages and an alert LED to give the alert indications. Now, let's look at the block diagram. As I said earlier, our mathematical model works by taking the value in the cloud. We use ThingSpeak to store the sensor value. We can retrieve data from ThingSpeak by using HTTP methods. In LabVIEW, we have HTTP client VI palette. It is a built-in VI palette which has many sub-VIs like OpenHandle VI, GetVI, etc. For establishing an HTTP request, we use the OpenHandle VI and GetVI. This is the HTTP request to get the last updated value. We give this URL as input to the GetVI. We get a string as output value which contains the created date, time, value, and field name. Since we only need the field value, we use a string subset function to select the substring which has only the field value. For doing calculations, we have to convert this into number. We use a decimal string to number function for this conversion. Now we got the last updated value. This field was to store the RPM of the indoor fan. Now we check whether the RPM is less than the set value. Here we check if the RPM is less than 800. If yes, the case structure for that is selected and an alert message is printed. The same steps are being followed to monitor the motor complaint. The only difference is that we use the reading from the temperature sensor, that is, the stored value in field 2 of our channel fan issues in ThingSpeak. Now let's see this work. We are changing the value in ThingSpeak by using a web browser. Let's run this by clicking the run button. We're going to open the browser and change the value in ThingSpeak Cloud. First, I'm going to give a fold value, say 90. As the RPM is set to 90, we see the field value is updated. As field value is updated, we can see the alert message is printed over there. Now, I'm going to give the correct value and change this back to normal. Likewise, I'm going to give a fault temperature value to field 2. I'm going to set the temperature to 90, that is greater than 45. As field value is updated, an alert message should be printed. You can see that alert message is displayed here. Now I'm going to change this back to normal. All conditions are back to normal. Let us see the filter module. This is the front panel of the filter module. The block diagram is almost the same as that of the fan module. We use an open handle VI, get VI, string subset function, and decimal string to number function in this module too. The functionalities are the same. We retrieve the values from the cloud that are sent by the IR sensor placed in the filter. We find average value, and if the average value is extremely low, it indicates that the filter is clogged and an alert message is displayed in the screen. Now, let's see this works. Since it is time consuming to change the values of 4 fields and do the demonstration, I have already set the values of 3 fields, and the last field value can be set to minimum or maximum for the time being. Now let's run the RapView program. Now we are going to change the value in ThingSpeak. We're going to update the value of the 4th field to 33. As we enter an extremely low value, we can see an alert message is printed over here. Refrigerant module. This is the front panel of the refrigerant module. Now let's look at its block diagram. The block diagram is almost same as that of other module. First, we retrieve the value from ThingSpeak. Here, the temperature from suction line is stored in field 5 of fan issues in our ThingSpeak channel, and we retrieve that value and check whether the temperature is between 50 degree Fahrenheit and 60 degree Fahrenheit. If the value exceeds, then we will print the alert message that the coolant level is not normal. Consult a technician. Now let's see this works. Let's run this LabVIEW program. Now we are going to change the value using the browser. We'll change the value of 5th field to 66. As the suction line temperature becomes 66 degree Fahrenheit, alert message is printed here. Now we'll change this back to normal. As the field is updated, coolant level become back to normal. Let's see the front panel of our main screen. This is how it looks like. We have an indoor filter alert, outdoor filter alert, coolant alert, indoor fan alert, outdoor fan alert, and thermostat alert. Now let's look at its block diagram. This is the block diagram. So now we are running this program. I'm going to change the temperature of suction line to 66 degree Fahrenheit. As the temperature field is updated, an alert message should be printed. Coolant alert is printed, and it will take a little bit of time to display the message. Let's wait. An alert message is also printed here. Now we will change this back to normal. The alert LED is turned off. Now let's try another one. We'll change the indoor fans RPM to 550 or 555. This field is updated. Indoor fan alert is produced, and the message is also printed here.
Next, we'll discuss about the effectiveness of proposed solution. Air conditioning systems are likely to have significant defects, and if not properly fixed, it can shorten the lifespan of AC by 10 to 15 years. It can also decrease the efficiency of the system, resulting in higher energy bills. The proposed digital twin Smart AC is designed to provide a real-time monitoring of the physical system. It checks and alerts the user following issues: refrigerant leakage problem, dirty filter problem, fan complaint issues. It also ensures effective working of the thermostat and auto configures the AC to an optimal temperature. Proper monitoring of thermostat is essential as its malfunctions can cause sudden changes in the performance of cooling system. Detection of fault before it's get active helps to optimize the performance, reduce the operational cost, and improves the quality of the system. In the present scenario, very little information is available on the methods to diagnose system and to detect these multiple faults. The proposed twin helps to identify intolerable deviations from optimal conditions and can predict the occurrence of any errors beforehand. Smart AC eliminates the uncertainties regarding the issue and lowers the need of human effort to detect the fault. AC technicians generally charge rupees 500 to 1000 per hour. Since a single maintenance can thus take up to 1 to 2 hours, amounting to rupees 500 to 2000 as service charge itself. Since our proposed Smart AC provides a clear information on the issue concerned and its cause, the time taken for troubleshooting the problem can be effectively reduced. If the fault occurred as minor, it can be fixed by the user itself, and our Smart AC provides step-by solution to do the corresponding actions. Since Smart AC includes temperature predicting module, the energy consumption can be optimized to about 10 to 15% through auto configuration and thereby lowering the electricity bills. This also helps to avoid the case of overcooling and frozen coolant issue. Next, let's discuss about the benefits of solution. For better understanding, let's take the scenario of not having the Smart AC. Refrigerant leakage is one of the major commonly occurring AC fault. The consequences of not having this fault being detected or diagnosed are: it can affect the system's efficiency and overall performance. It can lead to certain health hazards like breathing problems. It can cause increased bills, since refrigerant leak cause the air conditioning system to work harder to cool the home or office. The next problem is clogged air filters. The consequences which can occur by using the clogged air filters are increased energy consumption. When the air filter is clogged, air handler must work harder to compensate for the blockage of airflow. A clogged air filter can use 15% more of energy. For example, let's assume that the per day energy consumption accounts for rupees 100. An increase in 15% can make it to 5,400 rupees in an year. That is 15 into 30 days into 12. It can also lead to inadequate heating or cooling. Blower fans pull air through the filter. If filter becomes too clogged, the blower has to strain harder to pass air, leading to increased energy consumption. With reduced airflow, heating or cooling rate also decreases. It also contributes to unhealthy air. Clogged filter will allow dust and dirt to be recirculated back, causing chronic allergies. And you need to spend a lot of amount for the medication itself. A failure of AC fan can result in failure of entire system due to overheating. But if the fan complaint issue is detected in advance, such a situation can be avoided, saving up to about 20,000 rupees. Thermostat malfunctions can result in frequent short cycling or continuous running of the system. Continuous running of the AC affecting its overall performance in the long run. Since our smart AC is designed in such a way that it can monitor those areas vulnerable to faults and provides a clear information to the user about those parts that needs to be repaired. It can effectively reduce human effort and the time associated for spotting the faulty area. It can thereby save a lot of money. Next is the cost of solution. The first component to be considered is the temperature sensors. Then we are using three different types of temperature sensors, namely the LM35 temperature sensor, DS18B20 temperature sensor, and DST22 temperature sensor. The LM35 temperature sensor can cost, the cost can vary between rupees 59 to 250, and it has an accuracy of plus or minus 0.5. The DS18B20 temperature sensor can vary the cost from rupees 138 to 208, and its range is 55 degrees Celsius to 125 degrees Celsius. The DHT22 temperature and humidity sensor module can cost up to rupees 330. Since we use 4 modules, the total cost can amount to rupees 1,320. The effective temperature range is 0 to 50 degrees Celsius. The next component to be considered is tachometer. The RPM is, it can measure RPM up to 20K, and its cost is 1,200. Since we use 2 tachometers, it will amount to rupees 2,400. The next component is IR infrared obstacle avoidance sensor module. Its cost varies from rupees 51 to rupees 149. The effective distance range is 2 centimeter to 80 centimeter. Since there are 2 filters, namely the indoor filter and outdoor filter, we require a total of 8 IR sensors. We require a total of 8 IR sensors. The next component is Arduino UNO development board. Its cost is rupees 1,400. Then the average cost can account to rupees 5,600. But when the product is being commercialized, we can use other alternatives like microcontrollers, thereby reducing the cost. The next is ThingSpeak Cloud. It can amount up to, ThingSpeak Cloud is available for free for small projects and can send up to 8,300 messages per day. But when the product has to be commercialized, we need to purchase the license for the ThingSpeak Cloud, and it can cost up to rupees 15,000. But since a single unit can store a large amount of data, the cost of the product can be reduced to a large extent. Then the cost of the physical system, that is the air conditioner, it can start from rupees 20,000. Next is the project plan for building the working model. So this is the use case diagram of the entire smart AC, and we have divided the project to different modules, like namely the IR module, prediction module, fan module, and refrigerant module. The data from the IR sensors placed on the indoor IR filter, placed on the indoor filter as well as the outdoor filter are being sent to an Arduino UNO board. The Arduino UNO board collects the sensor data and uploads these data to a ThingSpeak Cloud via a Wi-Fi module. The ThingSpeak Cloud stores the sensor data, and these data is being retrieved by the Android app. The Android app serves several purposes. It has startup self-test unit, data analysis unit, and push notifications unit, contact support unit. The startup self-test unit performs the function of checking whether the integrated components are working properly or not. It does this function by checking the last updated date of the field values received from the ThingSpeak cloud. So by determining that, it can check whether our components are properly working or not. Next is the data analysis unit. The data analysis unit cross-checks the received values with the predefined set of values, and if the received values if the received values from the sensors does not fall under the category of our predefined set of values, it indicates that there is some error with the system, and the system push notification to the app user. Along with the notifications, we can add the stepwise instructions. For example, if the fault is a minor one and can be fixed by the user itself, the stepwise instructions can be really useful to do the steps. Then next is the contact support. For take the case if the fault detected is severe and cannot be solved by the user itself, then there is a provision to contact the support, to contact the maintenance crew. The user can either do that through the app or he can directly contact, but there's a provision inbuilt in our app to contact the maintenance crew. The next is the prediction module. First let me say what the prediction module do. The prediction module has DHT22 temperature sensors to measure the room temperature. The room temperature is measured, and based on that, an optimal temperature is being auto-configured for the AC. So this is how it works. For example, if the temperature is greater than 50 degrees Celsius, that is the room temperature is greater than 15 degrees Celsius, then the AC will be auto-configured to 16 degrees. Then as the temperature gets lowered, the AC is also auto-configured accordingly. The rest of the things are same, like the data is being passed to the Arduino Uno board, then to the ThingSpeak, to the Android app. Everything is the same. The next comes the fan module. The two faults which can occur in fan are motor complaint or capacitor complaint. We use the tachometer and LM35 temperature sensor. The tachometer is used to measure the RPM. If the RPM is less than the predefined value, then it indicates that there is some fault with the motor and it needs to be repaired. Then the LM35 temperature sensor, which is placed on the motor, and if its reading is greater than 40 degrees Celsius, it indicates that it is a capacitor complaint and it needs to be changed. So the readings from the temperature sensor as well as the tachometer is being given to the Arduino board, then passed to the ThingSpeak cloud, and then retrieved by the Android app, and the same steps like startup, self-test, data analysis, notification, the same steps are being followed as in the below cases. Next comes the refrigerant module. The conventional method for determining the refrigerant level is by using a PT chart. But here what we use is, we are placing the temperature sensor in the suction line of the compressor unit. Then if the temperature is between 50 to 60 degree Fahrenheit, it indicates that the refrigerant level is normal. But if it is greater than that, it indicates that the temperature refrigerant level is lower, and refrigerant level is lower, and there is some leakage issues. So the temperature sensor reading is being sent to the Arduino board, then to the ThingSpeak cloud. So this is the total working of a system. Thank you.